This is the physics unit of Science 30. We're going to start with topic 1.1, field lines. When we look at lightning, it's very mesmerizing. We find it in several different forms in the night sky. But why do we see it? Why do we have lightning? The reason that we have lightning is that it takes an enormous amount of water vapor in the atmosphere. And as that warm air floats up in the cooler surrounding area, as it rises up, the water vapor starts to condense to form clouds. The condensation releases energy, which causes the air to get even warmer and rise even higher. And then the warm air collides with condensed water droplets that's falling. The water droplets are holding on to their electrons a lot better than the rising water of the vapor. Lightning comes from the transfer of electrons. This is the symbol for electrons. From the falling water vapor to the rising water vapor, and then cooler to warmer, cold water colliding with warm water. Clouds become negatively charged and the surface of the earth is positively charged, and we know that opposites attract, and it's going to flow from the negative to the positive. Why is it so dangerous? It's dangerous because the amount of electrons that are being transferred is huge. It's 10 to the power of 18 to 10 to the power of 20 electrons, which is essentially this much. Electrons is a number that we can't fathom. And to make it easier to describe these effects, scientists use a special unit for charge, and that unit is called a coulomb. Coulomb is represented by the letter C, and 1 coulomb is equal to 6.25 times 10 to the 18 electrons. It's a unit for charge, and the symbol for charge is Q. So for example, if we're 6.25 18 times 10 to the power of 18 electrons gained, the charge on the object would be negative 1.00 coulombs, and if the electrons were lost, it would be positive 1.00 coulombs. When an object when the object gains an electron, it becomes negative. So as you get, and it's evident here, we get the negative sign there. So if you scuff your feet while walking across a carpet on a dry day, you can acquire a charge of negative 55 microcoulombs. The symbol here is micro, which means times 10 to the negative 6. Use the charge to determine if you gained or lost. Well, we have a negative sign out front, and we just said when an object gains electrons, it becomes negative. So we gained electrons. What happens to the charge on the carpet? As we gain the electrons, the carpet is losing them. Which means that the carpet, if we lose them, is becoming positive. Use the fact that 1.00 coulombs is equal to 6.25 times 10 to the 18 electrons to determine the number of electrons transferred while we were dragging our feet. This is really easy. We can set this up as an electron as a ratio. So we can say that 1.00 coulombs in 6.25 times 10 to the 18 electrons. And we remember up here that we were negative 55 microcoulombs. We have to pay attention to units. Negative 55 microcoulombs is equal to negative 55 times 10 to the negative 6. Remember, this is what micro means, coulombs. So we have negative 55 times 10 to the negative 6 coulombs. How many electrons would that be? And this is very easy. This is just cross multiplication. We're going to multiply 55 times 10 to the negative 6 by 6.25 times 10 to the 18. And then we're going to divide it by 1. So we're going to go negative 55 times 10 to the negative 6 coulombs multiplied by 6.25 times 10 to the 18 electrons in 1 divided by 1 coulomb. And this is how it's going to look on our calculator. We're going to make sure that we're using brackets. So we're going to go 55. And yes, I know there's a negative charge on there, but I'm not worried about the charge right at this moment. If you have a TI-83 or a TI-84, times 10 is represented by, if you go second and then EE, this little e here means times 10. And then I would put in my negative 6. I would multiply it by, and this is where brackets become really important, 6.25 second EE. And I say EE because there's two of them here, but you just get one up here. So 6.25 times 10 to the 18. And then I'm going to divide it by the 1. And I get 3.4375. And I see here that I have 2 digits, and here I have 3. The 2 is smaller, so I'm just going to go 3.4. My answer is going to be 3.4 times 10. This is that second EE. So it says 3.47 times 3.44 times 10 to the 14. E stands for times 10. On your calculator, this is the E. 14 electrons. Okay? So you're going to work on practice questions, pages 3 to 14, or page 314, questions 1 to 3. The answers are online for you to check. And then we're going to move down here to voltage. Another term for voltage is electric potential difference. And so it is the change in the amount of potential energy per unit or charge. And just by this very definition, the change, which is represented by the delta symbol, potential energy per unit or charge, so per charge. So that's where we get V is equal to delta EP over Q. Okay? Volts are measured in a joule per coulomb, so it's equal to 1 joule per coulomb. This is a joule, and this is a coulomb for units. And lots of times we say that joules equals the same language as work. I've done so many joules of work. Joules of work is equivalent to saying the potential energy. Okay? While scuffing your feet across the carpet, you do about 0.25 joules of work to acquire negative 55 microcoulombs of charge. Determine your voltage. So what's the information that I have? When we see this work, we can think of it as potential energy. So EP is equal to 0.25 joules. Charge is equal to negative 55 microcoulombs. And we're looking for our voltage. Things to pay attention to. Pay attention to your units. So I know that volts is found by EP per Q. So how do I change this Q to this micro to a regular? Remember, micro means times 10 to the negative 6. So over here, I'm going to have 0.25 joules divided by 55 times 10 to the negative 6. Remember that this means micro. And we get 0.25 divided by 55. Remember, times 10, second EE, negative 6. So that E means times 10 to the negative 6. And I get 4545. And the units for volts is joules per coulomb. An appliance in your kitchen is plugged into a socket that could provide the appliance with 120 volts and up to 15 coulombs of charge every second. If the cord for this appliance became frayed and you grabbed it with wet hands, calculate the energy that could be transferred to you in 1 second. So the information given to us, our V is 120 volts. Volts is the same as joules per coulomb. And our charge is 15 coulombs per second. And it's asking us to find the energy per second. We know the formula that we just learned is delta EP over Q. If I wanted to rearrange my formula, this is what I'm looking for. I'm looking for EP. So my first step is to get my Q out of the bottom. Because it's currently being divided, the opposite math function is to multiply. Since I multiplied it on this side and I have an equal sign, I have to multiply it on this side. When I rewrite it, I have VQ is equal to EP. And then I can go 120 volts multiplied by 15 coulombs per second will give me my EP. So 120 multiplied by 15 is 1800. And the units, here if we said that this was a joules per coulomb, because that's what we know a volt to be, we would see that our coulombs would cancel out and we would be left with 1800 joules for every second. So now you're going to work on practice problem number 4 on page 316. Pause the video and go do that work. There are 3 types of fields. You're going to use page 317 to 320 to help you describe these. I'm going to show you what they look like. So we always have a negative charge and a positive charge, or we can have positive plates and negatively charged plates if we put a battery in between. And we know that it flows out of the positive and it flows into the negative. So it flows from the positive to the negative. And what we see is if we have a negative charge and a positive charge, we see these lines go like this. Okay? So when we have a lightning bolt, and here's our Earth is positively charged. You may have heard in the past that lightning comes up from the bottom. What happens is it's this electric field, so the transfer of energy flows from the positive to the top, to the electrons. Okay? In the magnetic field, we have magnets. They have what we call a north and a south. Okay, when we're looking at a magnetic field, it flows from the north to the south. So from the north to the south. When we see opposites, because this flows out away from north, we see a repulsion. This is an attractive. Same with this one here. It comes in like this. And we see that these will also repel. Gravitational field if I was to put a satellite out in our atmosphere, and here's Earth, gravitational field always works towards the center of the object. And one thing to note for all of these, oh, you didn't see what I wrote. Sorry. The greater the density of lines, the greater the field strength. So if I had a very strong negative charge or a very strong magnet or a very strong object, these lines we would see quite a bit more. So something that might have less density, if this was the Earth, we could call this the moon, and we know that there is very, very minimal gravity field strength at the moon. So here's Earth with lots of gravity field strength, and here's the moon. And then if we were to look at Jupiter, it has an incredible gravitational field strength. So let's just do a brief summary of our electric fields. Electric fields have a property of space around a charge that enables the charge to exert forces on other charges. So that's the positive and the negative interacting, or the positive and the positive, or the negative and the negative, and we know that to be a repulsion. When clouds are charged right before a lightning strike, they're surrounded by an electric field, and that's where you get the tingling sensation, or sometimes a metal object will hum right before a lightning strike. And a test body provides evidence that an electric field is present. A charged object is surrounded by an electric field. In a magnetic field, it's a property of the space around a magnet or an electric current that allows the magnet or electric current to exert forces on magnets or electric currents, so like a motor. Compasses work because of the Earth's magnetic field. The Earth's magnetic field is believed to originate from electric currents that run deep within the Earth's crust. Or internal core, and electric currents and magnets can also produce magnetic fields. So that's why compasses tend not to work near anything that has a magnet. Gravitational fields, so these are, you can have a positive and a negative, positive and a positive, or a negative and negative. You can have a north and a south, a north and a north, or a south and a south. And we know that this is attractive and these are repulsive. This is attractive and these are repulsive. Property of the space around a mass that enables the mass to exert a force on another mass. So gravity pulls objects towards the center of Earth. And there are test bodies for gravitational fields or other objects within it. And the Earth exerts a gravitational force on all objects within its gravitational field. Okay. Field lines, so these are the lines that I've been drawing around it. These are invisible fields. We can't physically see the electric field. We can't visibly see the gravitational field. That's not true. We can see the electric field and the magnetic field in very unique times. We know those unique times. To see magnetic and electric fields, we call them the northern lights. Or aurora borealis. All right. This is just describing fields with diagrams, and we've already done that, so this is going to be quick. Gravitational fields, all objects with a mass have gravitational fields. Any object at or near the surface is the test body, and it's always attractive. There are no repulsive fields when it comes to gravity. Okay, here's an example of the magnets, north and south. You can see here that it flows away from north right here. You can see that it flows from north and into south. Okay. Compasses are typically the test body for a magnet. The field lines always leave the north end and enter in the south end. We've drawn this a couple times now, but here's the diagram that says it. And they have both attractive and repulsive fields. And magnetic, you can see here that it flows away from the positive and it flows into the negative source. Same thing if we were to have plates. You can see here electric fields under a thundercloud. This one here is much closer, so this is going to be more attractive, whereas these ones are farther away, so it's going to be weaker. Now you're going to work on practice problems on page 326, numbers 3 to 5. You'll find the solutions online in our Google Classroom.